Very happy to introduce John Chalker from Oxford, who will tell us about many-body delocalization as symmetry breaking.
Okay, thanks. So I've been looking forward to this meeting for well over a year, and I'm very glad that it's taking place, even if it's not quite in the format that most of us would probably prefer. And so thanks very much to the organizers. So what I want to do in this talk is to discuss the dynamics of spatially extended many-body quantum systems in terms of interference between different paths that the system can follow as a function of time in Fock space. And as you'll see, one of my main messages is going to be that in the ergodic phase, there's a form of symmetry breaking which appears within this description. And again, within this description, we can think of the phase transition to the many-body localized phase as a form of symmetry restoration. So I'd like to emphasize that this is joint work with Sam Garrett, who's finishing his doctorate in Oxford. And the work that I'll be talking about is all described in detail in two papers on the archive, which are due to appear soon. Oh dear. Right. So in outline, what I want to go through is, first of all, to introduce the models which I'll be using, which are Floquet quantum circuits, and then the language that I'll be using, which involves paths that are in Fock space. And then I'll talk about the many-body localization transition. And finally, I'll relate the more qualitative ideas that I give in the first part of the talk to a description in terms of a transfer matrix. And that's a transfer matrix that generates the spectral form factor by acting in the spatial direction in these extended many-body systems. So as I mentioned, I'll be talking about Floquet quantum circuits. So the picture is like this. If we're considering a one-dimensional system, then in the horizontal direction, I've got a lattice, and on each lattice site, I have some kind of generalized spin with Q states in the Hilbert space. And then I think about the evolution in real time, which is generated by some model unitary. And that unitary is built up out of gates which act on pairs of sites at a time. So in this picture, one Floquet period is the interval between these two dashed lines. So obviously, part of the motivation for considering models like this is simplicity, including simplicity when we want to do numerics. But I think you can also argue that in terms of possible universality classes for dynamics, there's a good case that systems of this sort include the very simplest universality class. And the point is that you would expect universality classes to depend partly on what conserved densities a system has. And if instead of a Floquet system, you considered a Hamiltonian system with a time-independent Hamiltonian and local interactions, then naturally you'd have energy density as one of your conserved densities. And if you're looking for an advantage to Floquet systems, then the advantage is that even energy is precluded as a conserved density because of the time dependence of the evolution.
Recording in progress.
So the specific model which I'll present numerical results for later on is this flock A system, which represents a kicked random field Heisenberg spin chain. And in this case, the two-site unitaries that couple neighboring spins are broken down into two factors. One factor is a standard Heisenberg coupling between adjacent spins, and the other factor is evolution of the spins on two sites independently in fields. And I'll have disorder in the system, so these field orientations and strengths are chosen randomly, and in the end I'll be interested in averages over an ensemble. And what you'd expect and what you find is that if the strength of the coupling between sites is below a critical value, then this model is in a many-body localized phase, whereas if it's above a critical value, it's in a thermal phase. So to characterize what's going on in these systems, I'll think entirely in terms of spectral properties. So of course, for the unitary evolution operator, we have eigenvalues distributed around the unit circle, and we can think about the spectral form factor, which is just the Fourier transform with time taking integer values as the Fourier transform variable of the two-point correlation function of the spectral density. And I'll use this notation a lot, where the integer times multiples of the flock A period stand simply for multiple applications of the flock A operator for a single period. So to remind people of some basics, if we on the one hand have a Poisson spectrum, so uncorrelated eigenphases, then the spectral form factor is simply a constant as a function of time. Whereas if we do a calculation for n by n unitary random matrices and average uniformly over the group, then at short times we have a linear dependence of the spectral form factor on time, reflecting level repulsion, and there's a time scale which is the Heisenberg time, 1 over the level spacing, and it's only at longer times that you go back to Poisson behavior. And when we go to spatially extended systems, we can see traces of both those types of behavior according to which phase the system is in. So in an MBL system, we see something close to Poisson behavior, and in an ergodic system, we see something close to random matrix behavior, and there are deviations at early times in the case of an MBL system on a time scale that's independent of system size, and in the case of an ergodic system on a time scale that you can call the Thouless time that grows with system size. And of course, when we compare random matrix results with results from a spatially extended system, we have the usual translation between the size of the matrix and the linear size of the system we're considering. So the kind of language which I want to use to discuss these problems is the language of paths in Fock space. So of course, normally when one talks about Feynman paths, one has in mind paths in phase space. And so I'm abusing terminology to talk about Feynman paths here, but nevertheless, what I mean is paths in Fock space. And for example, if we want to think about the amplitude to propagate in t time steps from an initial state to a final state, then we can expand that in terms of matrix elements of the flock A operator and think of the sum over intermediate states as being a sum over possible paths in Fock space. And one thing to emphasize about the notation is that when we think about a particular step in this path, it's a step in time, but of course to specify the location of that step in Fock space, we need to fix the orientations of the spins everywhere in the system on the time slice that we're referring to. So if you go from an amplitude to propagate between an initial and final state to a probability, then of course you have to deal with a double sum over paths, which I'm labeling P and Q. And a natural thing to try and do is to separate this double sum into some diagonal terms and some off-diagonal terms, which will have, in general, different phases attached to them. And the hope here would be that for one reason or another, these fluctuations may be unimportant. And for example, if we average over an ensemble of disordered systems, then maybe the fluctuations get suppressed. So there are lots of contexts where that kind of approach has been very useful. And the first one, I believe, historically, was in the semi-classical treatment of dynamics in low dimensions. So Goodsviller showed how to extract the spectrum of the semi-classical quantum system from periodic orbits of the classical Hamiltonian. And Berry showed how to understand spectral rigidity in terms of properties of isolated periodic orbits in chaotic systems. And then more recently, the theory of disordered conductors built on diffusons and couperons is basically a controlled theory of the fluctuations and the way that they combine with these diagonal terms. And in the last few years, in the context of many body systems, there have been several ways in which the diagonal approximation has been developed. So in work on random quantum circuits, you could think about the simplicity that comes there from saying that actually these are models that have been designed so that the diagonal approximation becomes exact. And then there are various many-body Floquet models which have been studied in particular limits, where again, the diagonal approximation becomes exact. And then finally, there's work which is really the successor to this early semi-classical work on low-dimensional systems, applying semi-classical ideas to many-body systems. So in other words, the diagonal approximation is a useful approach in lots of contexts. And when we go from simply the amplitude to propagate between an initial and final state and consider other physical quantities, then it may be that instead of having a single sum here, we have symmetry-related pairs of paths whose amplitudes interfere constructively. So if we go to the spectral form factor, then you can represent a computation of the spectral form factor since we have trace modular squared in terms of two closed paths. And the extra degree of freedom that we have is according to whether both traces start at the same origin or whether the origin for one trace is displaced relative to the other by either one time step or two time steps or more than two time steps. And so in this instance, by summing over the symmetry-related pairs of closed orbits, we get a simple understanding of the linear dependence of the spectral form factor on time that's familiar in random matrix theory. So when we go to spatially extended systems, one possibility that you can imagine if the coupling between sites is not too strong is that at short times, the system behaves more or less as if sites were uncoupled. And in that case, each site would contribute independently a factor of t to the spectral form factor. And on the other hand, at long times, the sites should all couple together, and we go back to the behavior for the spectral form factor that we would have expected from random matrix theory. And so it's the crossover between those two types of behavior that's what happens at the Thales time. And I want to talk about that within this language of paths. And to do so, I'll introduce some notation. So rather than representing the circuits as I have done initially on the left, since I'm interested in traces, I'll wrap the circuit up into a cylinder and no longer draw the individual gates. So the trace of the t-step time evolution operator will look like this. And when I go to a calculation of the spectral form factor, I'll have two concentric cylinders, one representing trace of W and the other trace of W star. And the central possibility that I want to talk about is that it could happen that you get spatial domains where in one spatial part of the system, we have one type of pairing between paths, and in a different spatial part of the system, we have a different type of pairing. And since within each domain we have T possibilities, then if there's some statistical cost associated with domain walls between different pairings, we have a kind of analogy, at least, with a T-state clock model with ferromagnetic interactions. So that analogy, or in fact an explicit mapping, is something that one can work out in a special limit where the size of the Hilbert space dimension is very large. And I worked it out with Amos Chan and Andrea De Luca a little while ago. I don't have time to describe that in any detail, but I'd like to pick out a few features from our results. So here I've just written the leading corrections to the linear dependence of the spectral form factor on time, the leading corrections at late times, which depend on the nature of the boundary conditions. So if we have periodic boundary conditions, then introducing a domain costs two domain walls, and hence this factor of e to the minus 2 epsilon t, whereas if we have open boundary conditions, we have a single factor of e to the minus epsilon t. And then there's also some entropic contributions from the locations of the domain walls, which grow with the spatial size of the system. And the point I want to make by giving these outline results is that, in fact, if you look at numerics on not the large Q limit where we can make the exact mapping, but rather a model with Q equals 2, then you see pretty much the same phenomenology. So these are graphs of the spectral form factor as a function of time, and the long time behavior is linear in time, but at early times there are deviations, and the deviations are larger with open boundary conditions than they are with periodic boundary conditions. And what's more, the deviations grow with increasing linear system size, as one would expect from these entropic factors. So the idea now is to try to formalize this kind of insight in a way that we can get a handle on from numerics and also relate to some larger description. And to get a handle on pairing domains from numerics, what one would like to do is introduce some kind of local order parameter which tells us, at least at a given site, whether the paths that are contributing to the trace of W are equivalent to the ones that are contributing to the trace of its complex conjugate. And we'd say we have perfect pairing at a given site if the spin state at that site in the one path is related to the spin state at that same site in the other path just by some shift in time. So in other words, we're trying to ask, according to the value of R, whether the paths look like this first example, the second one, or the third one, or to redraw the same point, if the state of the spin as a function of time in the path for W looks like this, what we'd like to do is identify whether the spin state in the path for W star trace looks just the same with some offset R. So we'd like to define an order parameter which has a phase that picks up the offset. And then in general, of course, there won't be a perfect match. So the amplitude should be something that tells us about the fraction of the spins that match between the two sequences. So formally, you can do this in terms of Kronecker deltas, which you weight with a phase factor. And then what we'd like to do is take these order parameters and compute averages in the sums over paths that tell us about the spectral form factor. And of course, if we just take a single power of the order parameter, then because we've got no symmetry breaking in the model, the result will automatically be zero. And so what we should do instead is look at 2-point functions in the usual way. And I'd like to emphasize that these averages, they're averages over the paths that contribute to these traces, and they're also, of course, averages over the ensemble of disordered systems. So one of our central results is this one, where we're looking at this 2-point function as a function of separation. On the one hand, in the thermal phase of the kicked random field Heisenberg model, and on the other hand, in the MBL phase. And so at least over the distances that we can explore in these numerics, it looks as if we do indeed have long range order in the thermal phase, and that order goes away when we go into the MBL phase. So what I want to do in the final 5 minutes or so of the talk is relate those ideas to some more general formalism, which I think gives a way of understanding sharply what issues are involved. And this more general formalism is in terms of transfer matrix, which generates the spectral form factor for the system by acting in the spatial direction. So the overall point is that we can compute the spectral form factor by contracting the tensor network either on time slices or on space slices. So if we consider the trace of the teeth power of the evolution operator, we're doing a contraction on a time slice, and the dimension of that trace, if we have L sites in the system, is q to the power L. But we can also take the contraction on successive space slices, and in that case, one of the traces will be of dimension q to the 4t. It's 4t because we've got two traces, and for each trace we need to take account of the state of the system at integer and also half integer time steps. And then if we're studying a disordered system, the individual transfer matrices in the first instance will be random, but after averaging over disorder, we have one fixed average transfer matrix for the spectral form factor, and we raise that to the power of the length of the system. And then in the usual way, the leading eigenvalues of this transfer matrix should be what determine the behavior of the spectral form factor. And then, of course, it's a standard idea that when we think about phase transitions in transfer matrix language, then the possibility of broken symmetry translates into the degeneracy or asymptotic degeneracy, in this case, at long times, of the leading eigenvalues of the transfer matrix. So the behavior which I will claim we find, and which we're working towards, is that in the MBL phase, this transfer matrix has a unique leading eigenvalue, and actually, in order for it to reproduce the behavior of the spectral form factor, then this leading eigenvalue must at long times be of size, the size of the local Hilbert space dimension, so 2 in our model. Whereas on the other hand, in the thermal phase, since the spectral form factor, when we get into the random matrix regime, is independent of system length, all of the leading eigenvalues that contribute should be unity in order that the L dependence here doesn't matter. And in order to have a spectral form factor that's of magnitude T, we need T degenerate leading eigenvalues. So our final point is to try and investigate some of this numerically. And actually, we need to go to rather large values of T. And that means that not only is it impossible to diagonalize the transfer matrix exactly, it's also impossible to use Lanczos techniques. So what we actually do is study the scaling with L of various quantities. And from that scaling with L, we can extract some information about the eigenvalues. And in particular, we have a good understanding of different symmetry sectors of the transfer matrix, and we know which symmetry sector the leading eigenvalue lies in. And by using appropriate boundary conditions, we can pick out that symmetry sector, and then studying a system with those boundary conditions, we can determine from the length dependence at fixed time the leading eigenvalue and later study its time dependence. And on the other hand, if we look at a system with periodic boundary conditions, then in the usual way, the spectral form factor is given by the sum of all of the eigenvalues raised to the power L. And so we can find how many eigenvalues are degenerate with the leading one. And the results that we get when we do this, well, firstly, if we pick out the leading eigenvalue by identifying its symmetry sector and studying length dependencies, then the different curves are colored according to the value of the parameter J that takes us through the phase transition. And in the MBL phase, we have a leading eigenvalue taking the value 2, as I said we should expect. And when we go over to the ergodic phase, the leading eigenvalue is 1 at long times, again, as I said we should expect. So the final thing is to count the number of other eigenvalues that at long times are degenerate with this leading one, which, as I said, we can do by comparing the spectral form factor in the system with periodic boundary conditions with the corresponding largest eigenvalue. And in the MBL phase, this ratio is unity, telling us that we have unique leading eigenvalue. And on the other hand, in the thermal phase, this ratio is simply at long times equal to T, which again tells us that we have, in this case, T-fold degenerate eigenvalues, which all approach unity at long times. So that's what I wanted to say. And so to summarize, I've tried to argue that a version of the diagonal approximation describes the thermal phase in these spatially extended many-body systems. And it involves a pairing of paths in Fock space, which in a sense constitutes a form of long-range order. And in that language, what happens at the MBL transition is loss of the long-range order. And I should make it clear that there are some limitations. So, of course, it would be very nice if we'd identified the pairing with some kind of physical observable. But unfortunately, that's not the case. It's really pairing in a language that's internal to the theory. And there are obstacles, at least as far as we see at the moment, to relating the pairing directly to the usual sorts of physical observables. But nevertheless, within the language of the theory, I think we have a way of thinking about the MBL transition that brings it closer to our descriptions of symmetry breaking phase transitions in other contexts. So thank you very much.
Thank you, John, for a very nice talk. Let's all unmute and applaud. And if anyone has any questions, please unmute and go ahead.
I can start with a question. Thanks. Can you hear me?
Yes.
Yeah. Thanks for the nice talk. So two questions. One, you mentioned, you talk about symmetry breaking. Can you clarify what is the symmetry you're referring to? Is symmetry related to those paths that you mentioned that you want to pair? And the other question is, what is Floquet? Is it Floquet important in all that? Or would you say that the same kind of symmetry breaking happens for unitary dynamics, time independent Hamiltonian?
Yeah, okay, sure. So for the first question, absolutely, the symmetry breaking is related to symmetries under the relative displacement of the origins of the paths that contribute to the trace of W of t and the trace of W star of t. So yes, it's exactly that, and you can be more formal, although I didn't have it on the slides. So as far as the second question is concerned, everything that we've been able to do so far is very much in the framework of these Floquet systems. So even writing down the transfer matrix that generates the spectral form factor is something which is straightforward to do within the Floquet context, and at least not at all straightforward imaging process if you go to a system with time-independent Hamiltonian. And obviously that's an important question, whether the same sort of ideas could be developed for systems with time-independent Hamiltonians, and I don't know the answer to that at the moment.
Thanks. Cool.
Hi, I have a question.
Please go ahead.
So hi, John. Yes, it's about a couple of slides. One of the last slides that you showed, the one with the plot of the, yes, this one. So it looks like you are able to achieve very, very large times here, if I understand correctly, because you go up to t equal 2 to the 8. So maybe I'm missing something, but it looks like this is a very large matrix, the one that you are dealing with. So how do you achieve this?
Sure. So the way we achieve it is by computing the spectral form factor, and we can compute the spectral form factor in the ways that you know very well for a system of limited length. So
yes.
I forget, but I think the system length here was 12. So that's the numerator in this expression. And then the denominator, well, what we do is, again, calculations in the time domain with boundary conditions, which mean that we couple only to the sector that contains the leading eigenvalue in the transfer matrix. And then we look at, well, what we get that way is an analog of the spectral form factor, and we look at its dependence on length. And obviously, you might or might not find that that was a good way of determining the leading eigenvalue. But what we do find is rather accurate exponential dependence on length. And so from that exponential dependence on length, we can get the leading eigenvalue.
So you see an exponential dependence on the accessible length?
Yes.
Okay.
Yeah.
Okay, thanks.
Sorry, I had a quick question, if that's okay. Can you hear me?
Yes.
This is Philip. You made a comment about the Potts model in your picture of sort of the tubes and sort of domain balls between the shift symmetry between paths. Is that an analogy that can be pushed? And can you say anything about the critical properties from this of the MBL transition?
Yeah, okay. So I need to make some distinctions. So in the work that Andrea and Amos Chan and I did, we had an exact mapping to, well, I think we said Potts model, but it really should have been clock model. And the mapping is that the partition function of the clock model is equal to the spectral form factor. But that exact equivalence is in this large Q limit. And there are lots of good reasons to believe that once we go away from the large Q limit, it's somehow a reasonable physical picture, but it's not the whole story. And the particular way in which I think it's not the whole story is that instead of having a statistical cost of domain walls, which is in the exponential linear in time, instead this domain wall tension would become a function of time. And then you asked about critical behavior. Well, if we're just discussing systems in one space dimension, then of course, in the clock model, we don't have a phase transition. And the fact that we only have long range order in the ferromagnetic clock model in the limit of 0 temperature corresponds to these domains only going away in the limit of long times in the quantum dynamics problem. But you can also ask what happens in higher dimensions, and the mapping to the clock model goes through there as well. And it means that one should be able to approach random matrix behavior for the spectral form factor much more suddenly and exactly in higher dimensional systems than in one-dimensional systems. So sorry, I didn't explain that very well, but it makes certain implications for the behavior of the Thouless time as a function of system size. Basically, the Thouless time should remain finite in the limit of large systems. But that's, of course, rather hard to check numerically.
Thank you.
Let us take one more question.
One question. Hello.
Please. Yes.
Okay. So it's a very naive question. So if I knew nothing about this, naively I would be tempted to associate MBL with onset of long-range correlations in time, right? Due to local integrals of motion. So I would rather naively think of the MBL transition in the opposite way around, as the formation of long-range order, right? So could you comment on this?
Well, of course, the long-range order that I'm talking about is in the spatial direction, whereas I think what you're advocating is long-range order in time.
Yes.
So those are perhaps two opposite possibilities. I mean, another comment is that actually the way that I've set things up is somehow more tailored to the ergodic phase, because if you go back to the introduction to the talk where I pointed out how from the diagonal approximation we get to the random matrix result for the spectral form factor, then the part of the random matrix result that we recover that way is the part where the spectral form factor varies linearly with time. And of course, beyond the Heisenberg time, we should get quite different behavior. So that different behavior is not captured by the diagonal approximation. And I think what you're pointing out we should be looking for in the MBL phase is probably closer to something beyond the diagonal approximation.
Yeah, thanks.
Can I ask one question?
Sure, go ahead.
Yes. Hello, John. So the group of Klaus Richter and Urbina studied in one of their works the Autok saturation in terms of for a boson system, Bose-Hubbard system, and they understood the Autok saturate the growth of the Autok at small times as the existence of a leading mean field solution, and then after a certain time these mean field solutions interfere, so the Autok saturates. Is that somehow related to, or can you understand that from the point of view of your work as the breaking of symmetry in one or another phase, or is it not really related?
Yeah, certainly I'm aware of that work. I haven't been able to make the kind of detailed correspondence that you're asking for. I mean, I suppose I should say that they studied some, reasonably physical model of, I think, bosons at large density on a lattice, whereas maybe we're focusing on a more idealized system with small Hilbert space on each side.
Okay, thank you.
Let's all press pause for now and thank John once again. According to the schedule, there's now a break. So as is the norm these days, let's all treat ourselves to a cup of coffee and maybe a pastry. And the conference will resume at 4 o'clock Paris time.